Yeah, welcome back to relation and function part 4. In part 3, we have studied what is function, what are some important functions and their graphs. Also, we saw the algebra of functions and we saw some types of function, one function, on two function and one on two functions. Let's see what is composition of functions. Let f is a function from A to B and g is a function from B to C. B two functions. Then, then the composition of f and g denoted by GOF, G of F. Composition F and G denoted by GOF, GOF, is defined as the function GOF is a mapping from A to C given by GOF of X is equal to G of Fx. Means F is operating first. That's why we take F from A to B and then G will take place from B to C. So ultimately we reach from A to B, then B to C. So we reach A to C for every X belongs to set A. If we see with the diagram, suppose Ax is any element in set A, then we will get Fx in set B, and in C, if we define, we can get G of Fx or Gx for every value, or Gy you can say. Then this function is F function actually. This is your G function actually, B to C, and you will get A to C as a GOF function. If we suppose Fx equal to some y, then your inside function will be Gy and it will be mapped from A to C only. B to C here. But as your Gy is a function from B to C actually. And G of Fx, if we suppose A to B, A to C will become, G to C will become, G of Fx will become A to C. A to C. Because inside function is also take a function, inside value is a function and that is coming from A to B. And G, if you operate on any particular value, it is from B to C. So ultimately you will get from A to C. Ultimately from A to C. So F is a function from A to B, G is a function from B to C, and their composition is function from A to C. Now you have two functions here. Remember, that's why it is A to C. If y is not a function, then it will be from B to C for any arbitrary y in set B. Let's see one example. Let f is a function from 2, 3, 4, 5 to 3, 4, 5, 9. And g is a function from 3, 4, 5, 9 to 7, 11, 15. The function defined as f of 2 is given you 3, f of 2 is 3, f of 3 is 4, f of 4 is equal to f of 5 is equal to 5. G of 3 equal to G of 4 equal to 7. G of 5 equal to G of 9 equal to 11 is equal to 11. Find golf. Find golf. Let's see the solution. If we see, this will work as a set A, this will work as a set B, this will work, it will be B again, and it will be C. So golf is going to be ultimately A to C. So golf of fx is equal to g of fx for every x belongs to A, and A is equal to 2, 3, 4, 5. So we have to check all these four values. So for x equal to 2, we will get golf of 2 is equal to z of f2, and f2 is equal to 3, so g of 3 is equal to 7. So first value will be 7. For x equal to 3, it will be golf of 3, it will be equal to z of f3. F3 is your 4, g of 4 is 7. For x equal to 4, if you check, you will get golf at 4 is equal to g of f of 4. F of 4 is equal to 5, and g of 5 is equal to 11. And last, for x equal to 5, g of f equal to 5, g of f of 5, f of 5 is again 5, g of 5 is 11. G of 5 is 11. So ultimately you are getting golf as a to C, it means 2, 3, 4, 5, 2, and your C will be your same 7, 11, 15. This will be the codomain, but range will be the elements 7 and 11 only. If you ask what is the range of golf, it is 7 and 11 only, but codomain is 7, 11 and 15. 7, 11 and 15. Remember, this is a very important point. One important property is, one remark is, composition is not commutative. Golf is not equal to fog in general. Means it does not hold the commutativity. Let's see one example. Find golf and fog, FOG, if f is a function from real to real and g is also function from real to real, are given by fx equal to cos x and gx equal to 3x square, so that f and g are not commutative. Let's see the solution. G of fx is equal to g of fx, and g of fx is nothing else cos x. Let's assume this is as a p, so it is gp. Gx is 3x square, so gp will be 3p square. Or you can write 3 cos x whole square, or you can write 3 cos square x. Similarly, if you find a f of g for any value x, so it will be f of gx, and gx is 3x square. Suppose this is your q, then it will be f of q. F of q will be, fx is cos x, then f of q will be cos q. If you put q is equal to 3x square, you will cos 3x square. And you can see that these two values are not equal for all x, not equal for all x. So composition is not commutative. Let's see some more remarks on composition. If f is a function from A to B and g is a function from B to C, are 1 to 1 and 1 to 1, then golf from A to C is also 1 1. 1 1. If f and g are 1 1, then their composition will be also 1 1. We have a more definition that is called identity function. A function is called to be identity function I from x to x. I'm writing from x to x, from a set x to x, which domain and the codomain is same. And generally we represent as ix, means this is identity function on set x. If it is given as I of x equal to x, means for every x the value is same, then this function is called identity function, and the notation it says that it defined on set x, and its a domain and range both are same. With the help of this identity function, I'm going to define a new function that is called invertible function. Let's see. A function f from x to y is defined to be invertible if there exists a function g from y to x. Remember this word, y to x, such that g of gof is equal to the identity function on x, and fog is equal to the identity function on set y. In that case, the function g is called the inverse of function f and denoted by f inverse. In this scenario, always remember, in this scenario, for existence of invertible function, f from x to y will be 1 1 and on 2. That condition, only these two conditions is going to be satisfied. On 2 means range of function is equal to the codomain of function. So range must be equal to y here. So this is the definition of inverse function. And for the inverse function, the condition is function must be 1 1 and on 2. For proving a inverse function, you have to check these two conditions. Let's see one example. Let f is a function from natural number to y be a function defined as fx equal to 4x plus 3, where set y is defined as collection of all y, where y is equal to 4x plus 3 for some x coming from natural number, so that f is invertible. Find the inverse. Let's see the solution. For proving invertible function f is invertible, we have to prove bijective 1 1 on 2, 1 1 and on 2. So first case I am going to prove f is 1 1. So for 1 1, we take two different images, x1 and x2 belongs to natural number, but their images, pre-images, two distinct pre-images, x1, x2 in natural number, but their images are equal. So fx1 equal to fx2 means 4x1 plus 3 equal to 4x2 plus 3. So x1 equal to x2 means function is 1 1. Now our aim to prove onto. F is onto. For onto, we have to prove that there exists a x for every y. For every y means for every image we have a pre-image. So for this we know the trick. Let fx equal to y. So we have to find x in terms of y here. So it will be 4x plus 3 equal to y. So x is going to be y minus 3 by 4. Now for general x equal to y minus 3 by 4, you find y minus 3 by 4 is equal to, it will be, fx is given as 4x plus 3. So if you put x equal to y minus 3 by 4, you will get y minus 3 by 4 plus 3, you will get y only. It means for image y, we have pre-image y minus 3 by 4. If y belongs to real number, you will get y minus 3 by 4 in a natural number. So we are taking such y only which are satisfying this property. The function y is given you. Y is not everyone. Y is set as given as this one. It is equal to 4x plus 3. Now, if you put x equal to 1, then y will be your 7. If you put x equal to 2, then y will be 11. If you put x equal to 3, y will be 15, and so on. Now, if you put any value, if you put 7, you will get 7 minus 3 by 4. So, 7 pre-image has 1, 11 pre-image is 2, 15 pre-image is 3. Means for every element you are getting pre-image. So, the function is onto also. For every element you have a pre-image, so function is onto here. It means f is both 1 1 and onto. Therefore f is invertible. Now for finding f inverse, how to find f inverse? For f inverse, let f inverse is equal to p. Now our aim to find this p. F inverse is p, so x is going to be f of p. What is your fp? Fx is 4x plus 3, so fp will be 4p plus 3. So p will be x minus 3 by 4. This is equal to f inverse only. So f inverse is given as x minus 3 by 4. X minus 3 by 4. Yes, one article I missed in set theory. I am going to discuss here, and this is the last topic, symmetric difference of two sets. I missed this topic in the set theory, symmetric difference of two sets. Let A and B are two sets, then their symmetric difference. This notation some books follow this notation. Is given as A minus B union B minus A. So this is the definition. A minus B I have already told you, B minus A I have already told you in the set theory. So this definition I skipped, I missed in the set theory. So please remember this also. Okay, so this is the ending of set relation function from my side. Next I'm going to start mathematical induction. Next topic will be on mathematical induction. Okay, thank you.